how do you discover something that nobody has, ever actually seen?
Which is, yeah, a pretty wild premise to start with.
Right. And I don't mean something you're actively looking for because, uh, I don't know, you caught a blurry photo of it on a telescope or something.
No, definitely not.
I mean, discovering something without a laboratory sample, without finding some strange colored crystal down in a mine, or, doing a chemical experiment. Just pure mathematical patterns and like a wildly bold prediction.
It honestly sounds like magical thinking when you frame it like that, but it actually represents one of the most profound paradigm shifts in the entire history of science.
And that is exactly our mission for today's deep dive.
Hmm.
We've gathered this really fascinating stack of sources for this one.
Yeah, quite a variety.
We've got historical chemistry archives, Dmitri Mendeleev's original 1869 papers, right through to like modern semiconductor physics journals and metallurgical data.
It's a huge span of time in science.
It really is. So we're unpacking the absolutely incredible story of element 32, which is germanium.
Germanium, yeah.
This is an element that was practically predicted into existence long before anyone could actually hold it in their hands.
Which is, it's a complete inversion of how we usually think about scientific discovery, right?
Yeah.
Historically, you find the rock, you analyze the rock, you name the rock. That's the order of operations.
The standard formula.
Exactly. But this is a detective story that fundamentally changed how we understand the very building blocks of the universe.
Picture a massive jigsaw puzzle just, spread out on the table in front of you. You've got pieces scattered everywhere.
A total mess.
Right, a total mess.
Ah.
But you are so good at understanding the pattern of the picture that you can look at one empty spot on the table and just know the precise details of the missing piece.
You can basically see it even though it's not there.
Yes. You know its exact shape, the colors on its edges, how it locks into the pieces next to it. And you know all this long before you finally find that actual piece hiding under the couch.
That analogy, that hits the nail on the head. But to really appreciate the magnitude of this, we kind of need to travel back to the 19th century.
Set the scene for us.
So look at the scientific landscape around the year 1869. At this point in history, chemists were discovering new elements left and right.
Like a scientific gold rush.
That's exactly what it was, a complete gold rush. But they were really struggling to understand the relationships between all these new elements.
They just had a lot of data.
Tons of data, a massive pile of it, actually, but absolutely no unifying theory to tie it all together.
So it's basically just a giant list of ingredients for the universe, but nobody has the recipe book yet.
Precisely, just a list. Enter Russian chemist Dmitri Mendeleev. He was developing what would, eventually become the modern periodic table.
Right.
And his approach was just entirely different from his peers. Instead of just listing the known elements by their atomic weights like some simple inventory clerk.
Which is what everyone else was doing, right?
Yeah, pretty much. But Mendeleev focused heavily on the repeating patterns in their chemical properties. He noticed that if you organize them by weight, elements with similar behaviors showed up at these really regular periodic intervals.
Okay, but think about the sheer arrogance of what he does next.
Oh, it's bold.
In literally any other field, if your data doesn't fit the model you're building, you throw out the model.
You have to.
You don't just stand up and say, well, the universe is missing a piece to make my spreadsheet work.
No, you definitely don't say that.
Yet, when Mendeleev's patterns pointed to an element that didn't exist in any lab anywhere in the entire world, he deliberately left a gap in his table.
He literally left a blank space. And, you're right to point out the audacity of that. It was a spectacularly confident move.
I can't even imagine the pushback.
Well, he recognized that the periodic table wasn't just a filing cabinet. It wasn't just an arbitrary list. It was a reflection of a hidden natural order.
A map of how things actually are.
Exactly. And if the geometry of that order dictated a piece should be there, it must exist. The surrounding elements practically force the geometry.
Okay, so how did he know it was a legitimate gap and not just, a flawed pattern? How did he account for all the unknown variables?
Well, he triangulated it. He looked at a specific empty space right below silicon on his table, and he boldly predicted a missing element that he named Eka-Silicon.
Eka-Silicon, okay.
Right. But he didn't just stop at saying, hey, an element is missing here. He systematically analyzed the surrounding elements. So he looked at silicon above it, tin below it, gallium to the left, arsenic to the right.
Looking at the neighbors.
Exactly. By averaging their properties, he constructed this highly detailed physical and chemical profile of this ghost element.
I was looking at the sources on this, and the numbers he put down are honestly mind-blowing.
They are so precise.
Let's be really clear for you listening right now.
Yeah.
Mendeleev did this without any modern computer modeling. There was no algorithm crunching the numbers in the background.
Nothing like that at all.
This was pure, systematic, deductive reasoning done with pencil and paper.
Pure deduction. And he was incredibly specific. I mean, Mendeleev predicted that this missing Eka-Silicon would have an atomic weight of 72.
Just throws a number out there.
Yeah, and he predicted its density would be 5.5 grams per cubic centimeter. He even detailed how it would react with oxygen and chlorine, predicting the exact density and boiling points of those hypothetical compounds.
That is wild. That is genuinely like studying a family tree and predicting the exact height, eye color, and like bone density of a cousin you've never met, just by averaging the traits of their relatives.
That's a great way to put it.
But here's the thing. After he published this incredibly specific profile in 1869, he just had to wait.
And the wait was grueling.
I bet.
The scientific gamble here really cannot be overstated. Predicting something with zero physical evidence in 19th century chemistry, that was practically asking for ridicule.
But the whole vibe back then was just observation, right?
Exactly. The empirical tradition was to observe first, theorize second, to theorize first and say, well, the observation will eventually catch up. That created a huge amount of tension in the scientific community.
Put yourself in the shoes of a skeptical scientist of that era. Like, what if the missing element simply wasn't there?
Right. What if he's just wrong?
We see patterns in the clouds all the time, you know? That doesn't mean there's a literal castle floating up in the sky.
Yeah.
If Eka-Silicon didn't exist, it meant Mendeleev's beautiful, elegant pattern was just a coincidence.
And the whole foundation of the periodic table as a predictive tool would just crumble.
It would all fall apart.
Yeah, and that skepticism lingered heavily for 17 years.
Wow, 17 years.
17 years of waiting until 1886. And this is where the story shifts to a German chemist named Clemens Winkler.
Okay, Winkler enters the chat.
Right. And what's really fascinating here is that Winkler wasn't even trying to solve Mendeleev's puzzle.
He wasn't looking for Eka-Silicon.
Not at all. He was just studying a rare mineral called argyrodite, which had recently been found in a silver mine.
So Winkler wasn't actively hunting for the missing element. He was literally just doing his day job, running a standard, albeit complex, chemical analysis on a rock.
Exactly. He expected to find a specific combination of familiar elements, mostly silver and sulfur in this case. But as he ran his quantitative tests and, tallied up all the components, the results didn't add up to 100%.
They were off.
Yeah, he kept coming up short by about 7%. There was this unaccounted for residue. The math of the mineral was fundamentally broken based on known chemistry.
I love this part of the scientific process so much. He just stumbled into a math problem that wouldn't resolve while doing routine work. The universe's ledger just wasn't balancing.
And most people might just write off a 7% missing chunk as, I don't know, a contaminated sample or experimental error.
To sweep it under the rug.
Right, but Winkler was a meticulous detective. He dug in, he isolated that mysterious residue through this really grueling series of chemical separations, and his work led to the extraction of a brand new chemical element.
Which is amazing.
It is. And he named it Germanium, honoring his home country of Germany.
Okay, so Winkler finally isolates element 32. He's actually holding this new physical material in his hands. And then the scientific community tastes Winkler's hard physical data, and they hold it up next to the predictions Mendeleev made 17 years earlier for Eka-Silicon.
And the match sent absolute shockwaves through the scientific world.
I mean, I would hope so.
Remember those predictions? Mendeleev predicted an atomic weight of 72. Winkler measured germanium's atomic weight at 72.6.
That is incredible.
Gets better. Mendeleev predicted a density of 5.5 grams per cubic centimeter. Winkler measured germanium's density at 5.47.
That way.
Yes. Mendeleev predicted the oxide of this element would have a density of 4.7. Winkler found the actual oxide density was 4.703.
Okay, that is just showing off at that point.
It really is.
But this causality, this is what actually matters here. Because Winkler's data perfectly matched Mendeleev's mathematical ghost, it forced chemists to accept that Mendeleev wasn't just making a convenient list. He was seeing the actual hidden structure of nature itself.
It proved that Mendeleev's model was fundamentally true. I mean, before 1886, the periodic table was largely seen as just a classification system.
Like a neat way to organize things we already knew about.
Exactly. But after Winkler found germanium, the periodic table became a predictive scientific tool. It literally became a map of reality itself.
Wow.
It gave scientists immense confidence to trust the map, even for the territories we hadn't explored yet.
But the hard data that Winkler published didn't just validate the periodic table. It forced scientists to look really closely at the bizarre physical traits of what he had actually found.
Oh, yeah, because germanium is strange.
Yeah, element 32 is weird. What exactly was Winkler looking at when he had it?
Well, if you had a chunk of germanium sitting on your desk right now, it would be silvery white. It looks very metallic.
Like steel or something?
Yeah, if you just glanced at it, you'd think it was a piece of standard steel or tin. But germanium is actually a metalloid.
Meaning it sits right there directly on the boundary line between metals and nonmetals in its chemical behavior.
Yes, and that gives it physical properties you wouldn't expect just by looking at it. For example, common metals like copper or iron are malleable.
Right, you can bend them.
Exactly. You can shape them, draw them into wires. That's because metals have a structural lattice that shares this fluid sea of electrons, allowing the atoms to kind of slide past one another without breaking the bonds.
Okay.
Germanium doesn't do that. It is incredibly brittle.
Because it doesn't have that fluid sea of electrons, right, it forms a rigid covalent network, like a diamond lattice.
Exactly like diamond.
So a standard metal is like a flexible net. It moves and stretches with you. But germanium is bonded like a rigid scaffolding. If you hit it, it doesn't bend. The joints just snap.
That's a brilliant way to visualize it, yeah. It looks like a tough metal, but it shatters like glass. However, its most important trait isn't really how it breaks mechanically.
It's the electricity part.
Right, it's how that rigid covalent electron structure behaves electrically. That structure gives germanium its massive hidden superpower.
And that superpower being that germanium is a semiconductor.
The original semiconductor, really?
Now, I know you listening are probably well aware of what a semiconductor is conceptually. It's the foundation of all modern electronics that can selectively gate electrical current. But what we really need to look at is why germanium specifically was the absolute star of the early 20th century electronics boom.
Yeah, when scientists were developing the very first transistors back in the 1940s, germanium was the go-to material.
Transistors being basically tiny electronic switches.
Exactly. And germanium was chosen because its band gap, which is the amount of energy required to push an electron from a resting state into a conductive state where it can flow, that band gap was relatively low.
So it was easy to trigger.
Right. It was low enough to be manipulated easily and reliably with the early technology of that era. Germanium completely ushered in the era of solid-state electronics, replacing those bulky, fragile vacuum tubes everyone used to use.
Which is amazing. But it definitely leads to the obvious elephant in the room here.
I know where you're going with this.
If germanium was the superstar that kicked off the electronics revolution, and its band gap was so perfect for early transistors, why do we live in a world defined by Silicon Valley?
Yeah, why isn't it Germanium Valley?
Exactly. Why isn't the tech capital of the world called Germanium Valley?
It really all comes down to thermal instability.
Heat.
Heat, yeah. As technology evolved, engineers wanted more processing power. That meant packing more and more transistors into smaller and smaller spaces. And when you run electrical current through millions of microscopic switches packed tightly together, you generate a massive amount of heat.
And this is where the atomic structure of germanium becomes a massive liability compared to silicon.
It does.
Because they sit right next to each other in the same column on the periodic table, so they have similar properties.
Yeah.
But germanium is heavier.
Much heavier, yeah. Germanium has 32 electrons spread across 4 electron shells. Silicon, sitting right above it, only has 14 electrons spread across 3 shells.
All right, so germanium's outermost valence electrons, the ones actually responsible for conducting electricity, they're physically further away from the nucleus than silicons are.
Exactly.
So the electromagnetic grip holding them in place is just weaker.
And that weak grip is its downfall in high heat environments. When a germanium chip heats up from all that processing power, the ambient thermal energy is actually strong enough to knock those loose outer electrons right across the band gap.
Meaning they start flowing on their own just because it's hot?
Just from the heat, yeah.
And if electrons are flowing uncontrollably, you've completely lost the ability to selectively gate the current. The switch is basically just stuck in the on position.
Exactly. It stops acting like a semiconductor and just becomes a leaky, useless conductor.
Wow. So silicon just holds its electrons tighter.
It does. It requires a lot more energy to cross that band gap, which means it can operate reliably at much higher temperatures without leaking current.
That makes total sense.
So as we pushed for large-scale, high-power, modern computer chips that run super hot, silicon was simply better equipped for the physics of the job.
It's wild to think about, really. Your earliest digital devices owe their entire existence to this ghost element, even if silicon eventually swooped in and stole the spotlight.
It really did.
Germanium built the house, and silicon just moved in and took all the credit.
It definitely did. And well, silicon is obviously much more abundant in the Earth's crust as well, which helped them scale the industry massively.
Sure, cheaper and easier to find.
But don't feel too bad for germanium because it never actually became obsolete.
No.
Not at all. In fact, it is experiencing a massive modern resurgence right now, specifically because of the exact same chemical bond properties we just talked about.
Right. The sources actually highlight its current use in cutting-edge applications, particularly in infrared optics.
Yeah.
It's heavily used in thermal imaging, night vision, specialized scientific cameras.
Yes, and the chemistry behind this is fascinating. If you try to build a lens for an infrared camera out of regular glass, it won't work well because glass absorbs a lot of infrared light.
Oh, interesting.
Yeah, the molecular bonds in glass actually resonate with those specific infrared frequencies, which ends up blocking them. But remember germanium's specific covalent lattice and its band gap.
Right, that rigid diamond-like structure.
Exactly. Because of how its electron structure is arranged, low-energy infrared photons just don't have enough energy to excite the germanium electrons across that band gap.
Oh, this is fascinating. So the infrared photons just pass right through unabsorbed.
Exactly. I mean, that is the core mechanism there. To visible light, a piece of germanium looks like an opaque block of metal. You can't see through it at all.
Like a brick.
Just a shiny brick. But to an infrared camera, a germanium lens is completely transparent. It perfectly transmits those thermal wavelengths, which makes it absolutely essential for high-end optical systems.
So it got pushed out of computing by silicon and ended up literally helping us see in the dark.
Pretty great second act.
Seriously. And on top of that, it's quietly powering our massive modern communication networks, too.
It is, yeah. Germanium is heavily used in fiber optic technology. The core of the optical fibers that carry all our internet data around the globe often contains germanium dioxide.
Really?
Yeah, doping the glass with germanium changes its refractive index, which helps efficiently guide the light signals over vast distances without losing the data.
That's wild. And the ultimate irony here is that germanium and silicon actually ended up teaming up in the end.
Oh, the alloy. Yes.
After the great betrayal in the computer chip market, modern engineers figured out how to just alloy them together.
They did, and by combining silicon and germanium, engineers can create materials with unique electronic properties that neither element can achieve on its own.
The best of both worlds.
Exactly. Silicon-germanium alloys are used heavily today in high-speed integrated circuits for wireless communications. That includes the radar systems in modern cars and the high-speed tech right inside your smartphone.
The journey to Element 32 is honestly staggering when you step back and look at the whole picture.
It really is a unique story.
It wasn't just found by someone swinging a pickaxe in a mine. It was predicted into existence. A missing space in a mathematical pattern became a highly specific physical profile.
Right.
That prediction waited 17 years through immense scientific skepticism to become a laboratory experiment. And that experiment by Clemens Winkler revealed a new physical reality that proved the underlying structure of our universe.
It's a powerful reminder that science isn't just about cataloging the things we can already see.
No, not at all.
It's about having the vision and the mathematical rigor to understand what we can't see yet. I mean, Mendeleev discovered germanium just by looking incredibly closely at the gaps in the data he already possessed.
It started as a mathematical ghost, built the foundation of early solid-state electronics, got benched by its lighter cousin silicon, and is now just quietly powering our infrared lenses and high-speed wireless tech.
It's an incredible legacy, and if you connect Mendeleev's periodic table to the bigger picture of science today, it leaves us with an incredible question to ponder.
Oh, absolutely.
Mendeleev's map had gaps that pointed to hidden physical truths. Today, we have new maps of reality. We have the standard model of particle physics. We have cosmological models where 85% of the universe's mass is categorized as dark matter.
Which is essentially a massive gap in our understanding.
Exactly. It's a huge blank space on our current map. So as you navigate our modern world, which is just bursting with data, we really have to ask, what are the germaniums of our generation?
What fundamental truths are hiding right now in the empty spaces of our current scientific models?
Just waiting for someone to notice the pattern and predict them into existence.